So what I'd like to do is look at some limits as x goes to infinity. So notice x is getting really, really big here. Sometimes we're tempted, we see denominators, we look at them and we think, oh, wait, let's factor and cancel stuff if we can. There's no need to in this case, because if I take a huge number like, a million or 2 million or anything really big, as big as I can imagine, and sub it in here, it's not going to make this fraction undefined. So to solve this, like I said, you can use something called an end behavior model, or an EBM. That's how I'll abbreviate them. And to get one, all you do is you take the highest power term on top and divide it by the highest power term on the bottom. So if you do that here, take this term, divide it by that term, watch what happens. You get 117 over x squared over negative 9 over x squared. Well, if we take a look at that, what we notice is the x squareds cancel, and you're just left with 117 over negative 9. Well, it turns out that's the answer to the limit. So if you think about how we introduce this topic, let's rewrite this same limit. Limit as x goes to infinity of 117 x squared plus 150x over 100 minus 9. So in yesterday's class, what did we do? We looked for the highest power of x, and we multiplied everything by that, or the reciprocal of that. So 1 over x squared over 1 over x squared, right? And when we did that, what we noticed is that the things with the highest power just became numbers, well, in this case at least, and here you get plus 150 over x. So it sort of shows you why x squared is the most powerful term in the numerator. So when I multiply through, these things, for example, anything over x, like this one's going to be 100 over x squared minus 9. And what you'll notice is this term here and this term here, as x gets really big, these guys go to 0. But these guys are unaffected by that, right? So what I noticed is, or what you can notice is, and why EBMs work, is that if you look at this problem, what we know when we multiply through by 1 over x squared, this 117 will be left behind, this 9 will be left behind, this negative 9, but these guys are going to end up going to 0. They're not going to matter anymore. So this is sort of a quick way to do that. Now, this helps you out a lot with problems where sometimes the highest power on top and the bottom are different. So look in this problem, for example. EBM equals highest power term on the top, 117 over x squared, and the highest power term on the bottom is negative 9x cubed. So this time, what's not going to happen is this. It's not going to cancel completely to a number. By the way, 117 over negative 9 is negative 13. But here when you reduce, you get 117 over 9. That becomes negative 13. And on the bottom, there's still an x left over. So now you need to do a little bit of additional thinking. You need to ask yourself what happens as x gets really big. If x becomes really, really large, what happens to negative 13 over x? So this gets closer to 0, and that's your answer, 0. Okay? So at least for these first two limits, let's just briefly discuss what these look like graphically. What I know is, in the first function, as x goes to infinity, which means I'm going real far to the right, I'm over here on the right side of the x-axis, the y values I get are getting closer and closer to negative 13. So the graph maybe does something like that. It comes down and levels off at y equals negative 13. That's the meaning of a limit as x goes to infinity. We can look at this on the calculator. So we just got to remember this function here. Here we go. So y equals, come on, okay, we'll get rid of that thing. So open parenthesis, it was 117 x squared, I believe, plus 150x, close parenthesis, divided by open 100 minus 9x squared. All right, that looks good. Okay, so what we're going to do is we're going to start with, we can kind of see the picture down here, but down here on the bottom. Let's look at the graph, and here we go. That's what we get. Seems a little strange to me. Let me go back to y equals for a minute. All right, so 150x, 117x squared. There we go. Plus 100 minus 9x squared. Okay. So I just checked this. Let's take a look at the window. Let's look at the. Let's change the window a little bit. Now, obviously, we know from our limit that our limit as x goes to infinity was y equals negative 13. So I'm going to go for a y min of something like negative 15. And since I'm interested in what happens when x gets really big, I'm going to take x max. Instead of making it 4.7, I'm going to try making it a bigger number, like maybe 100 maybe. And let's see what happens. Ah, there we go. So now we look at the graph. What we start to see is the following. Looks like something's lost here, but it's not. So here's what you have. This up here is where that parabola used to be that we were looking at, that parabola-looking thing. And this is actually another piece of the graph that we haven't seen before. So there it is. It looks like we just had a parabola. There's actually more pieces down below, lower in the y direction. So let's not forget what we're interested in here. We're interested in the limit as x goes to infinity, which means I'm moving really far along to the right in this direction. And as I do that, what I'll notice is that the y values down here seem to be leveling off. And actually what they're leveling off at is y equals negative 13. So that is the geometric interpretation of a limit as x goes to infinity. It tells if you get a number like negative 13, it means that's where the graph is leveling off. Okay? All right, so we now have a geometric interpretation of a limit. It would be fair to ask now, how come when we get a limit like this, 117x squared plus 150x over 100 minus 9x squared, how come we can just use an EBM, this EBM thing, that's going to be the highest power term on the top divided by the highest power term on the bottom, or in this case, negative 13? Well, the reason this works is because this thing here and this thing here get, I won't say closer and closer together, but they behave the same way when x gets really big. You can kind of convince yourself of that. Imagine I plugged in a number like 10. So I plugged in a number like 10. 150 times 10 is 1,500. But when I plug 10 in here, that's 100 times 117, right? There's now 100. Yeah, right? So it's 11,700. So 11,700 is much bigger than 1,500. Now, if you go for, say, plugging in 1,000, right, this becomes 150,000 over here, but this thing becomes 117 million. So it really starts to dominate, right? This term here, this first term, is growing much faster as x gets larger than this term is. So for large values of x, this term on the right here doesn't matter. This thing, you can just sort of forget about it. Okay? And then for the same reason, if x is really huge, look at the bottom. I mean, 100 has no chance. 100, we always thought it was like a big number when we were younger. No chance. Start plugging big numbers in here. Plug in, here you go. Plug in 1,000. 1,000 squared is a million times 9 is 9 million. 100 minus 9 million is basically negative 9 million. It's about that. It's 100 away from it. But this 100 does nothing. It loses the battle. So what we say is the end behavior model sort of says, hey, what's the most powerful term on the top? What's the most powerful term on the bottom? And just divide those, figure out what those do, and you'll know what the limit is. That's why these things work. Now, there was one more limit I wanted to finish here. This one on the bottom, sort of special. By the way, actually, just a quick comment about this problem. What that graph is doing is, as x gets really big, y is getting closer and closer to 0. So maybe this graph does something like that. It levels off at 0. So in the first two cases, we had what I'm going to call horizontal asymptotes, HAs. Both of those graphs leveled off as I moved really far to the right. Okay, so a fair question might be, I decided to draw this such that it seems to be approaching y equals 0 from below. So the question someone might want to ask is, hey, how come you don't know it goes like this maybe? Maybe from above it comes in and levels down. Well, if you start putting big numbers in here, think about negative 13 divided by a huge number, maybe, right? Well, that's going to be some kind of decimal that's close to 0, but it's also going to be negative because you have negative 13 divided by positive a million in this case. And then as I made x in the denominator get bigger and bigger, I'd be taking a number like negative 13, dividing by bigger and bigger positive numbers, which would give me a negative decimal that's closer and closer to 0. So that's how I know the graph must be like the bottom one. It must be coming up from below and leveling off at y equals 0. Okay? All right. This last question, let's do an EBM and see what happens. So N behavior model. Here we go. 117x to the fourth over negative 9x cubed reduces to negative 13x. Okay. So what you'll notice is, again, I have an x in my N behavior model. So now I got to do a little bit of thinking again. So here we go. If x gets really big, if I plug really big numbers in here, the question is, what kind of numbers do I get back? Right? Well, negative 13 times a huge positive number is basically going to be negative infinity. It's going to become more and more negative. Okay. So here we go. This last function's a little bit different from the other two. The other two had horizontal asymptotes. They leveled off at y equals negative 13 or y equals 0. This graph doesn't do that. What this graph does is, as I go really far to the right, y goes down really, really far. So the graph's got to do something like this. So be careful sometimes with these limits. And I'll say this. I could just change one thing. Suppose I said what happens is x goes to negative infinity in this same problem. It was 117x to the fourth plus 150x over 100 minus 9x to the third. Well, your EBM is still the same. It's just like what we did before. It's negative 13x. Right? But now watch what happens. Now I start taking numbers that are very negative and putting them in here, like negative a million, negative a billion, negative a trillion. And as I do that, when I multiply them by negative 13, I get numbers that are larger and larger. This actually becomes positive infinity. So what does that mean? It means that on the graph, we saw that as x went to infinity before, y became negative infinity. What we just learned is, though, is as x goes to negative infinity, as I go really far in this direction, y actually goes up to infinity. So maybe it goes up like that. So here's having said all this, here's a fun question to consider. Let's look at the three limits. And the question I want you to think about is, could you look at a function, like look at the things I'm circling in red, could I have looked at them and right away said, oh, some of those are going to have horizontal asymptotes and some aren't, without doing much work at all? You could sort of predict what's going to happen with the N behavior model. In the first case, the two highest powers were equal. So that means they're going to cancel, and you're going to get just a number for an answer. So you'd have a horizontal asymptote. In the second case, the higher power is on the bottom. So when you got your N behavior model, it was going to have x in the denominator. But we already know if you take really big numbers and plug them into a denominator, that usually makes a fraction get smaller and smaller and smaller. I should say not smaller, but closer and closer to 0. Okay? And then this last case, the higher power is on the top. So the higher power is on the top. When you divide, you're going to have x in your numerator now. So now I start putting large numbers in there. That x is going to get really big. And I'm probably going to end up multiplying it by something. Just watch out for the SIGN, the sign of that thing, right? Because it might be negative instead of positive like it was in this case. Let's take this one step further. So in the problems we did, they were easy because we could just look at exponents, like 2 verse 2 and 3 verse 2 and so forth. But what about a limit like this? Limit as x goes to infinity. And then suppose you have something like this, like x to the fourth plus 2 to the x over 117x to the third plus 1,000. Now you want to go find your EBM. And when you write EBMs and behavior models, we have to think about what term in the numerator is the most powerful term. Well, you'll need to know something about exponential functions when compared to power functions. Okay? So when you have just a number as an exponent and a variable base, that's called a power function. That's what this thing is. And this one's called an exponential function. So generally, if you have an exponential function like 2 to the x here, for big values of x, if x is going to get big and go to infinity, 2 to the x will win when you compare it to x to the fourth. Now you might say, how do I know that? Well, years of experience, I'll tell you. But try plugging in some numbers. For example, try plugging in 2. You plug in 2, 2 squared is 4, and then 2 to the fourth is 16. So it looks like this guy's winning. When x is 2, you get 4 is greater than 16, and that's not true. So why am I saying this? Well, I'm only claiming it works for really big values of x. So let's try a bigger value of x. Try like x equals, I don't know, let's say 10. Let's see, 2 to the 10th versus 10 to the fourth. Well, 10 to the fourth is 10,000. But what's 2 to the 10th? So, I thought this was going to work. It didn't. Uh-oh. No good. My claim is it's going to catch it. Let's try x 2 equals, say, 50. I don't know if the calculator will be able to handle this, but let's try 2 to the 50th power and compare that to 50 to the fourth power. Let's see what we get. So if you type this in the calculator, this is about 1.12 times 10 to the 15th power, and this is somewhere in the 6 millions. So just so we're clear, this is not exactly 6 million. It's close to it. It's in the 6 millions. Either way, this number is much, much bigger. So what you'll notice is, as x starts to get here, look, we're just at 50 right now. If I go out to x equals 1 million or 2 million or something like that, 2 to the millionth power is going to be much bigger than 1 million to the fourth power or something like that. So you can see how exponential functions win. So I'm telling you this because when you go to find the EBM of a problem like this, 2 to the x is the thing you're going to choose from the top because it's going to beat anything. And in case you're interested, even if this had been x to the 400th power, it still wouldn't matter. 2 to the x eventually will win. It might take longer to do it, but it'll win. Okay? Versus on the bottom, you have 117x to the third. Now what you'll notice is that this is not going to reduce. So the question now becomes, what happens to this thing as x gets really big? Well, we just discussed, when x is really big, when x is going to infinity, that 2 to the x will beat any exponent function, anything that's just a power function. So we know the top is going to get bigger much faster than the bottom, so that means the answer is infinity. And this graph has no horizontal asymptote in the positive direction. What that means is, as I go really far to the right, this graph shoots up to positive infinity. So you have to be pretty careful with these kinds of problems. So I'm going to take the same function, but ask a different limit. I'm going to say, what's the limit as x goes to negative infinity of this thing? Let's just remember what it was there. Okay, so x to the fourth plus 2 to the x over, I think it was, what was it, 117 x to the third plus 100 or 1,000 or something. Doesn't even matter. Okay, yeah, I got it right. So now we're going to do an EBM again. And here's where it's a little bit subtle. If we head towards negative infinity, then we have to be very careful with a function like 2 to the x. Now, in order to figure this out, we need to remember what happens when we put a negative exponent on a number. So let me remind you, 2 to the negative 1 is 1 over 2. 2 to the negative 2 is 1 over 4. Oh, that's right, right? Negative exponents mean we flip the base. So, for example, we had 2 to the negative 10. That means 1 over 2 to the 10, or 1 over 1,024. So now what happens is this. If we're going to head in the negative direction, then this thing here is heading towards 0. It's becoming 1 over 2 to a really large power, which means that the EBM is going to change now. When we go to negative infinity, the most powerful term on the top now is x to the fourth. And that's different than when we were going to positive infinity. Okay? Because when we head in the negative direction, 2 to the x becomes something very close to 0 and it's not powerful anymore. The bottom, no worries there, 117x cubed. And I can divide this and proceed the old way. So x over 117. And then I just need to ask myself, if x becomes very negative, what happens to this thing? Well, if I take a very, very negative number and divide it by 117, it's still very, very negative. So the answer is negative infinity.